So in this video, we're going to go over a few more questions to practice our mole calculations. Let's take a look at a small pin that contains 0.0178 moles of iron. How many atoms of iron are in the pin? So first of all, I want to point out the number of significant figures here. We have 1, 2, 3. So our final answer should have 3 significant digits since that's in the question. Let's use the guess method. Let's look at what's given to us. We have the number of moles is given to us. So N is equal to 0.0178 moles. And then we also have, don't forget, Avogadro's number, which is 6.02 times 10 to the power of 23. I usually put it in brackets because I like putting my scientific notation in brackets. And that's going to be Fe atoms or particles per mole. So particles is replaced by Fe atoms in this case. And what are we looking for? We're looking for how many atoms there are. So the number of particles we're looking for is N. In other words, number of atoms total. So we're looking for N. And so what equation are we going to use? Well, if we're looking for big N, we know that big N is equal to moles times Avogadro's number. And so we can go ahead and substitute and solve. So we're going to do big N is equal to number of moles, which is 0.0178 moles, times 6.02 times 10 to the power of 23 Fe atoms per mole. And that's the proper conversion factor, right? So conversion factor here, we're doing the moles to particles. So we're doing 6.02 times 10 to the power of 3 over 1 mole per 1 mole. And so we can cross out moles and moles there, and we're left with atoms. And so we can go ahead and try that in our calculator. We would get 0.0178 times 6.02 times 10 to the power of 23. And I get 1 point, or let me put N is equal to 1.07156 times 10 to the power of 22 Fe atoms. And then we're going to have our therefore statement, that third S there. Therefore, the number of particles is equal to approximately to a correct number of sig figs, which is 3 sig figs. So 1, 2, 3 sig figs. Look next door here, and we're rounding down. So we're going to have 1.07 times 10. Whoops, I think the ink dried out. Let's retry that. Times 10 to the power of 22 Fe atoms. And that is our final answer with our therefore statement. Let's try another example. Let's try example number 3. So we have a sample of bauxite ore contains 7.71 molecules of aluminum oxide. How many moles of aluminum oxide are in the sample? So here it's going to be a bit different. Let's write down what our given information is first. Given, this time we have the number of molecules, or I should say particles. So N is equal to 7.71 times 10 to the power of 24. Al2O3, I think I should have really said formula units there, but I said Al2O3 molecules. And we also have, don't forget, Avogadro's number, which is, so I'm putting these in brackets here, 6.02 times 10 to the power of 23 Al2O3 molecules per 1 mole, per mole. Okay. And you could have just written the mole without any, so that's fine to shorten it. And what are we looking for? Well, we are looking for the number of moles. And so we know that our equation for the number of moles is going to be N is equal to N over Na. In other words, we're using our other conversion factor. We're using the 1 mole over 6.02 times 10 to the power of 23 particles. So when we want to go from number of particles to number of moles, we're using that other conversion factor. So we're going to substitute and solve. So we're going to get that N is equal to the number of particles, which is 7.71 times 10 to the power of 24 Al2O3 molecules over 6.02 times 10 to the power of 23 Al2O3 molecules per mole. And so what I want you to see here is that the units will still cancel out the way you want them to. You have molecules canceling out here, molecules canceling out here, and moles over here. Notice how you have a line over a line. What that does is it causes your mole to go back up to the denominator at the end. So you end up with moles as opposed to moles being at the bottom, sorry, to the numerator at the end. So we're crossing out molecules, we're ending up with moles, and so let's just do that in our calculator here. We get 7.71 times 10 to the power of 24 divided by 6.02 times 10 to the power of 23. And so we get that N is equal to 12.80730897 moles. Of course, we can't leave it like that because we have to round to the proper number of sig figs. There are 3 sig figs in the question that's given, 3 sig figs. So we'll round that to 3 sig figs. So therefore, number of moles is equal to approximately, so 1, 2, 3 sig figs there. Look next door, we're rounding down, 12.8 moles, and that's 3 sig figs. I just want to show you, you could have done this using the conversion factor method, which is basically what we did here, but you could have done, so this is other method using conversion factor. So if we did that, you would have done 7.71 times 10 to the power of 24 Al2O3 molecules and multiplied it by the conversion factor of 1 mole over 6.02 times 10 to the power of 23 Al2O3. Let me just write that to have more room here. Otherwise, it's very messy. Times 6.02 times 10 to the power of 23 Al2O3 molecules. So we have 1 mole for that many molecules. And so you'd cross out your molecules and you're left with 1 mole. And in the end, you're still dividing as we did earlier. So we'd be 7.71 times 10 to the power 24 divided by 6.02 times 10 to the power 23, and you get your final answer over here as well. So they're equivalent methods of doing it. It's just you need to show your formula for one, and it automatically gets you to that division. Whereas with the conversion factors, you're setting up the conversion factor and then afterwards multiplying and dividing. So that there is the example where we use the different version of the formula where we want to find the number of moles rather than the number of particles. In the next video, we'll do examples 4 and 5. You should try it yourself and then compare with the next video to see that you're on the right track.